Hello everyone. Let's start with a simple thought. When we say an object has an area of 2 square meters or a mass density of 1000 kilograms per cubic meter, how do we actually know what these quantities mean in terms of physics? The secret lies in their dimensional formulae. The dimensional formula of a physical quantity expresses it in terms of the three fundamental quantities: length, written as L, mass, written as m, and time, written as t. To derive it, we relate the given physical quantity to other quantities whose dimensions are already known. For example, area equals length multiplied by breadth. Since both are length, its dimensions are L multiplied by L, which equals L squared. In this way, every physical quantity can be written systematically as powers of L, m, and t. And once we know the dimensional formula, we can also deduce its C unit. Let's begin with the simplest, geometrical quantities. Area is the product of length and breadth. Both have the dimension L. So, area equals L multiplied by L, which equals L squared. The dimensional formula becomes m to the power 0, L squared, t to the power 0. The C unit is square meter. Volume is length multiplied by breadth multiplied by height. That is L cubed. So its dimensional formula is m to the power 0, L cubed, t to the power 0. The C unit is cubic meter. Notice here that both area and volume do not involve mass or time. They depend purely on space. They are spatial quantities that measure extent in 2 and 3 dimensions.
Now, let's look at density, velocity, and acceleration. Density is defined as mass divided by volume. Mass has the dimension m and volume has L cubed. So density equals m divided by L cubed, which is written as m to the power 1, L to the power minus 3, t to the power 0. The SI unit is kilogram per cubic meter. Velocity is displacement divided by time. That is L divided by t, giving the dimensional formula m to the power 0, L to the power 1, t to the power minus 1. The SI unit is meter per second. Acceleration is change in velocity divided by time. Since velocity is Lt to the power minus 1, dividing again by t gives Lt to the power minus 2. So its dimensional formula is m to the power 0, L to the power 1, t to the power minus 2. For example, if a car goes from rest to 20 meters per second in 10 seconds, its acceleration is 2 meters per second squared, perfectly matching the dimensional formula Lt to the power minus 2. Now let's turn to quantities that directly connect to Newton's laws. Force equals mass multiplied by acceleration. That is m multiplied by Lt to the power minus 2. So force has the dimensional formula m to the power 1, L to the power 1, t to the power minus 2. Its SI unit is the Newton. Work is force multiplied by displacement. Force is mLt to the power minus 2, displacement is L. So work becomes mL squared t to the power minus 2. The SI unit is joule. Kinetic energy has the formula 1/2 mv squared, that's mass m multiplied by velocity squared. Since velocity is Lt to the power minus 1, squaring it gives L squared t to the power minus 2. Multiplying with m, we again get mL squared t to the power minus 2. Potential energy equal to mgh also reduces to mL squared t to the power minus 2. So both kinetic and potential energy share the same dimensional formula as work, highlighting the principle of conservation of energy. Next, let's explore pressure, stress, and power. Pressure equals force divided by area. Force is mLt to the power minus 2, area is L squared. Dividing, we get mL to the power minus 1t to the power minus 2. The SI unit is Pascal. Stress is also defined as force per unit area, so it shares the same dimensional formula, mL to the power minus 1t to the power minus 2. Power is work divided by time. Work is mL squared t to the power minus 2. Divided by t gives mL squared t to the power minus 3. The SI unit is watt. In real life, pressure explains everyday experiences. A sharp knife cuts better because the area of contact is smaller, which means the pressure is greater for the same applied force. Let's now work through an advanced example together. The dimensional formula of the universal gravitational constant, G. From Newton's law of gravitation, force F equals G multiplied by m1 multiplied by m2 divided by r squared. Rearranging gives G equals F multiplied by r squared divided by m1 multiplied by m2. Now substitute the dimensions. Force F has the dimensions mLt to the power minus 2. Distance squared is L squared. Mass squared is m squared. So G equals open bracket mLt to the power minus 2 close bracket multiplied by L squared divided by m squared. Simplifying gives m to the power minus 1 L cubed t to the power minus 2. Thus, the dimensional formula of G is L cubed, m to the power minus 1, t to the power minus 2. The SI unit is Newton meter squared per kilogram squared. As you can see in the diagram, two masses separated by distance r attract each other with a force F, and G is the constant that sets the strength of this universal attraction. Let's quickly recap the key points. Dimensional formula expresses a quantity in terms of the fundamental dimensions L for length, m for mass, and t for time. For example, area is m to the power 0, L squared, t to the power 0. Density is mL to the power minus 3. Force is mLt to the power minus 2. Work and energy are mL squared t to the power minus 2. Pressure is mL to the power of 2, the power minus 1t to the power minus 2. Every physical law can be checked dimensionally. If the left-hand side and right-hand side have the same dimensions, the equation is consistent. Dimensions provide a universal tool to connect, verify, and understand the relationships between physical quantities. I hope now you clearly see how dimensional formulas are the backbone of all derived units in physics. In our next session, we will explore how dimensional analysis can be used to derive new relations. Until then, keep questioning and keep discovering the beauty of physics in daily life.